we're being asked to find a vector function for the intersection curve between these two quadric surfaces. The first thing that we should do is try to graph these two. And even if you don't remember the general form of this quadric surface and what it's supposed to look like, we can still generate the graph without too much difficulty. I notice that if I were to plug in constant z values here, if these were simply numbers, the cross sections would end up being ellipses. And hopefully that's something that we recognize from previous courses. So what I'm going to do is I'm going to just plug in constant z values. Let's let z equal to 4. And essentially z equal to 4 is a plane. And what we're looking at is what would this quadric surface look like, or what kind of an intersection curve would we have in that z is equal to 4 plane? Well, we plug 4 into the actual equation, so we get 4 is equal to 4x squared plus y squared, and I recognize this as being an ellipse, so the standard form of the equation of ellipse can be determined by dividing both sides by 4, and I end up with x squared plus y squared over 4. So we end up with an ellipse in that plane where I'm traveling 1 in the direction of x and 2 in the direction of y. So within this z is equal to 4 plane, I'm going to travel 1 unit in the direction of x and 2 units in the direction of y and draw a plane curve which is an ellipse. And then we can do this again in a different plane. So I'm going to come down here, and instead of letting z is equal to 4, this time I'm going to look at a different plane, and I'm trying to keep my numbers fairly easy for the computation. I'm going to look at the z is equal to 1 plane. So essentially we're wondering, what does this quadric surface look like in the z is equal to 1 plane? In order to determine the intersection between two surfaces, we plug one into the other. So we're plugging z is equal to 1 in, we get 4x squared plus y squared. We already have our desired positive 1 on one side of the ellipse, so we just need to fix up this right-hand side. Instead of saying times 4, I'm going to say divided by 1/4, which is the same thing, in order to see how far I'm traveling in the direction of x on this ellipse in that plane. And in the direction of x, I'm traveling the square root of the number underneath the x, which is 1/2. So I'm going 1/2 in the direction of x and 1 in the direction of y in this z is equal to 1 plane. So we could keep doing this, slicing with different z-planes, but I can already see the pattern is that I'm getting ellipses in these planes as I slice this quadric surface. So let's connect these ellipses, and what we're going to end up with is an elliptical paraboloid as our quadric surface that's coming up like this. As far as the other quadric surface is concerned, let's notice in the equation that we're missing a variable. And if we're missing the z value, that means we start by graphing the two-variable equation in the plane of the two variables that are present, in this case x and y, and we recognize, of course, this is a parabola opening up, or essentially wrapping around the y-axis. So let's try to take this 2D curve and put it into the xy plane in the floor of our three-dimensional space. So here is our parabola in the xy plane that's wrapping around the y-axis, and then we get to extend this in the direction of z. So we're basically taking this parabola and flying up and down with it. So we're going to kind of create this parabola again up in a higher z-plane, and then envision that we're getting this quadric surface here that results from flying this parabola up and down in the direction of z. And this continues infinitely in both directions, but I'm just kind of drawing it above the xy plane here. So now it's time to find the intersection curve between these two surfaces. What we want to do is take one criteria or equation and literally plug it into the other criteria so that we come up with one equation that satisfies both of these requirements. So we end up with z is equal to 4x squared plus y squared is going to become, we're going to plug in x squared in for this. And our equation then now depends only on x, 4x squared plus x to the fourth power. When we have our equation depending on x now, we can come up with parametric equations for this merged criteria equation. And as we know, there's infinitely many different ways to do that, but the easiest thing to do is just to let x equal to t. And if x is equal to t, then z is going to be 4t squared plus t to the fourth power. And let's recall from the original equation that y was equal to x squared, so then y is going to have to be equal to t squared. And that's all we need to come up with our vector function. I'm going to use pointy bracket notation this time, and these parametric equations literally become the components of the vector function. So the x component is t, the y component is t squared, and the z component is going to be 4t squared plus t to the fourth, and this is the vector function that traces out the curve C that is the intersection between the two surfaces described above. We'll check our answer in GeoGebra now. So here we are in GeoGebra, but of course any 3D graphing software is going to work. And we're going to plug in, first of all, let's look at our surfaces that we originally started with. So z is equal to 4x squared plus y squared. And thankfully we can see that our surface that we originally drew was correct with elliptical cross sections in the constant z planes. And our second equation was y is equal to x squared, which turned out to be a parabolic cylinder. Now, it's hard to see when they're both the same color, so I'm going to come over here to the settings, click the three dots and go to settings, color, and change the color of that elliptical paraboloid. I'm going to go to dark blue here, and then we X out, and we see a little bit better that intersection between these two surfaces. To check our answer, what we'll do is we'll put our vector function for that intersection curve into GeoGebra. We could use r, which is the variable that we used in our computation. Lowercase letters is what tells the software that we're talking about a vector when we open up that parens, and then we'll say t is the x component, t squared was the y component, and 4t squared plus t to the fourth power was the z component. And then we simply see if that curve appears to be the intersection of the two surfaces. And look, it's showing up in this black. But yes, our curve looks to be exactly on the intersection between those two surfaces. And that's how we can tell that our vector function is correct.